Chapter 3: Force and Pressure. Learning Objectives. Moments, turning effects of force. Balancing moments. Pressure, units of pressure. Application of pressure in daily life. Atmosphere or air pressure. Liquid pressure, pressure exerted by gases. Measuring pressure. Every day we utilize the turning effect of forces, moments, for example, when we use devices such as levers. However, in some cases we require to prevent the turning effect of forces by balancing them with an opposing movement. Understanding the principles involved allows us to both utilize and prevent the turning effect of forces. Moments, turning effects of forces. The turning effect of a force around a fixed point, a pivot, is called moment. For example, a door opening around a fixed hinge or a spinner turning around a fixed nut. The size of a moment depends on two factors: the size of the force applied, the perpendicular distance from the pivot to the line of action of the force. This explains very less force is needed to open a door by pushing at the side furthest from the hinge than at the side closest to the hinge. To push at the hinge side of the door requires more force to be exerted because the distance is smaller. A moment can be calculated using this equation: M is equals to F multiplied T, where M is equals to the moment of the force in Newton meters, and F is equals to the force of newtons, and D, the perpendicular distance from the line of action of the force to the pivot in meters, m. Worked example. A spanner is used to undo a nut. A force of 35 Newton is applied to the end of the spanner, which is 10 cm away from the center of the nut. Calculate the moment when the spanner is horizontal. 10 cm is equals to 10 divided by 100 is equals to 0.10 meter. Moment is equals to force multiply perpendicular distance. Moment is equals to 35 multiply 0.10 is equals to 3.5 Newton meter. Balancing moments. When an object is not turning around a pivot, the total clockwise movement must be exactly balanced by the total anti-clockwise movement. We say that the opposite movements are balanced. Sum of the clockwise movements is equals to sum of the anti-clockwise movements. Seesaws. A seesaw has a pivot in the middle. A person on the right exerts a force downward, which causes a clockwise movement. The person on the left exerts a force downward, which causes an anti-clockwise movement. If the people are identical weights and sit identical distance from the pivot, the seesaw will balance. This is because the total clockwise movement is balanced by the total anti-clockwise movement. The seesaw can still be made to balance even if the people are of different weights. To do this, the person with the bigger weight must sit closer to the pivot. This reduces the size of the movement, so the opposing movements are once again balanced. Cranes. Construction cranes lift heavy building materials using a horizontal arm called a jib. To prevent the crane toppling over, concrete blocks are suspended at the other end of the jib. They act as a counterweight to create a moment that opposes the moment due to the load. Levers. A lever is a simple machine that makes work easier to do. Examples of simple levers include cutting with scissors or lifting the lid on a tin of paint with a screwdriver. Levers reduce the force needed to perform these tasks. When someone uses a lever, they exert a force, the effect, around a pivot to move an object. The load. Levers rely on the principles of movement to act as force multipliers. They reduce the effort needed to move the load by increasing the distance over which it is acting. This means a relatively small effort has a much greater effort. The hammer. A hammer can be used to pull out a nail from a piece of wood. The load force is 50 Newton. and it acts at a perpendicular distance of 0.07 meter. Its moment is 3.5 Newton meter. 50 multiplies 0.07. The effort force acts as a longer perpendicular distance. This is 0.28 meter or 4 times the distance of the load force. As a result, the effort needed is 4 times less than the load force, or 50 divided by 4 is equals to 12.5 Newton. Note that the moment of the effort is 3.5. 12.5 multiplies 0.28, the same as the moment of the load. In this case, an effort force of 12.5 Newton is sufficient to pull against the load force of 50 Newton, making it relatively easy to pull the nail out. Pressure. We have already studied about force. Whenever a force is applied, there is an impact or effect of that force. This impact or effect that the force produces on an object depends on two factors as: first, the amount of force applied on the object. The greater the force applied, the greater is the impact. Second, the area over which the force is applied. If the force is applied on a greater area, the impact is less. The smaller the area of application of force, the greater is the impact. The effect of force acting on a surface gives the concept to pressure. Pressure is defined as the force per unit area and is expressed as pressure is equals to force upon area. For this question, it is clear that first, greater the force, greater is the pressure. Thus, the pressure is directly proportional to the force applied. Second, greater the area on which force is applied, smaller is the pressure. Thus, the pressure is inversely proportional to the surface area on which pressure is applied. Units of pressure. The SI unit of pressure is the Pascal, PA. Pascal is the pressure exerted by a force of 1 Newton, acting over an area of 1 meter square meter. Thus, the SI unit of pressure is Newton per meter square, or Pascal, or PA. 1 PA is equals to Newton per meter square. In CGS system, the unit of pressure is dyne per square centimeter, dyne per centimeter square. Some of the important applications of pressure in daily life are mentioned below. Application of pressure in daily life. First, a sharp-edged knife is always used to cut the vegetables, fruits, etc. The sharp-edged knife exerts more pressure because it has a smaller area of contact. Second, a needle with pointed tip is used for sewing the clothes. A pointed nail is put inside the wall. All of them exert more pressure due to smaller area of contact. Third, bags and suitcases are made with broad belts or straps as handles. Since the belts or straps are wider, they have a large area of contact. Hence, the hands feel less pressure and it causes less pain. Fourth, buses, lorries and trucks have double wheels at their rear. Lorries and trucks have double wheels at their rear to increase the area of contact so that the pressure exerted on the ground is reduced. Fifth, porters wear turbans on their head to carry heavy loads. The turban increases the area of contact, so less pressure is exerted on the head. Sixth, the high-rise buildings have broad and wide foundation to minimize the pressure exerted by the building on the ground. Seventh, war tanks move on caterpillar tire belts, which are broad and have a chain-like wheel cover. It increases the area of contact, so the pressure on the ground is minimized to a large extent. The tanks can move even on soft wet ground because of this. Eighth, the elephants have broad feet to exert the pressure and enable them to walk easily on the ground. Ninth, rails on the railway track are fixed to a large, wide wooden or steel slipper to exert less pressure on the ground. Atmospheric or air pressure. All gases exert pressure because they are always in motion. If the gases are confined in a container, the gaseous molecules exert pressure all over the walls of the container in all the directions such as top, bottom, sideways, etc. For example, after you fill air in a balloon. If you fill more air, the balloon will burst because the air exerts pressure on the walls of the balloon. The earth is surrounded by a thin layer of air called atmosphere. The force exerted by the atmospheric air in unit area is called atmospheric pressure. At the sea level, the atmospheric pressure is about 100 kilopascal, 10 to the power 5 Pa. The atmospheric pressure at sea level is called normal pressure or standard pressure. Since the blood pressure of human body is almost equal to the atmospheric pressure, we do not feel any pressure on our body. Atmospheric pressure decreases as the altitude increases. Since the blood pressure is more than the atmospheric pressure at high altitudes, bleeding starts from nose and ears as their blood vessels rupture. Similarly, a fountain pen leaks at high altitudes because the air inside the pen has more pressure than outside. Applications of atmospheric pressure. There are various applications of atmospheric pressure. Some of the applications are as follows. First, while drinking cold drinks or any other liquid with the help of a straw, the air inside the straw is sucked so that the air pressure inside the straw becomes less. Thus, the atmospheric pressure exerts pressure on the liquid in the gas so that the liquid enters into the straw. Second, similarly, atmospheric pressure forces the liquid to enter into the syringe when the air inside the syringe is taken away. Third, same procedures is followed in droppers as well. Liquid pressure. Liquid has the property of flowing freely from upward to downward direction and taking the shape of the container. The pressure in case of liquid is the force exerted by the liquid in unit area. Pressure is equals to force divided by area. The important characteristics of liquid pressure are: first, liquid exerts pressure in all the directions such as upward, downward and sideways. Second, the sideways pressure or lateral pressure at the same depth is equal in all directions. Third, liquid pressure increases with the increase in depth. Fourth, pressure of the liquid increases with the increase in volume of the liquid. Fifth, denser liquids exert more pressure than the less denser liquids. The pressure at the bottom of the water is very high. Therefore, to sustain the high pressure, the dams are made broader at the base than at the top. Pressure exerted by gases. All the gases exert pressure on the walls of the container. Air is a mixture of gases. All the gases are made up of tiny particles called molecules, which move around quickly in all directions. The fast-moving gas molecules collide with one another and with the walls of the container. Air pressure arises due to the constant collision of the tiny molecules of the gases present in the air with the walls of the container it is enclosed. If a certain mass of air is compressed into a smaller volume, then the number of collisions of air molecules per unit area increases and hence the pressure exerted by air goes up. If the container of air stretchable walls, then the higher pressure exerted by air inflates the container. Take a rubber balloon and fill air into it with mouth or by pump. On filling the air, the balloon gets inflated, expands and becomes bigger in size. When we put a lot of air in the balloon, then the number of gas molecules in the balloon increases too much. The large number of gas molecules cause too many collisions with the walls of the balloon from inside and create a high pressure, air pressure. This high pressure produced by the gas molecules on the walls of balloon causes it to expand and get inflated. When air is pumped into a cycle tube by using a pump, the bicycle tube gets inflated due to the air pressure exerted by the collisions of the gas molecules in air with the inner walls of the rubber tube. This air pressure in the bicycle tube makes the bicycle tire feel hard. Consider the molecules of a gas moving at random in a container as shown below. The molecules are continually colliding with each other and with the walls of the container. When a molecule collides with the wall, they exert small force on the wall. The pressure exerted by the gas is due to the sum of all these collision forces. The more particles that hit the walls, the higher the pressure. If a gas is heated up, its particles move around more quickly. They hit the walls of their container hard and more often. This increases the pressure. Sometimes the pressure gets so great that the container bursts. This is why balloons and tires burst if you blow them up too much. It's also why deodorant spray cans carry warning signs to tell you not to leave them in the sunshine. If they get too heat, they explode. Measuring pressure. Manometer is the device by which the pressure can be measured. A simple manometer consists of a glass tube fixed to a stand with a scale. The tube is half filled with a liquid, which is usually water. One end of the U-tube is open and the other end is attached to the tissue funnel, covered with a tight, thin rubber skin. When the tissue funnel is kept open, only atmospheric pressure acts on it, which is equal to the atmospheric pressure on the open end of the U-tube. Now, apply some pressure on the rubber skin by pressing it with your finger. As the pressure increases, the water level in the arm of the U-tube attached to the rubber tube goes down and water level in the other end arm will go up. Now read the difference between these two levels. This is the measure of pressure exerted on the rubber skin. Summary. The turning effect of a force around a fixed point is called moment. The equation to calculate the moment is M is equals to F multiplied D, when M is the moment of the force, F is the force in newtons, and D is the perpendicular distance from the line of action of the force to the pivot. Sum of clockwise moment is equals to sum of anti-clockwise moment. Pressure is force per unit area. The SI unit of pressure is Newton per square meter and N per meter square or Pascal PA, and in Celsius unit dyne per square centimeter, dyne per centimeter square. The pressure exerted by air is called atmospheric pressure. The greater the force, the greater is the pressure. The greater is area, the smaller is the pressure. The liquid exerts equal pressure in all the lateral directions at the same depth. The pressure of liquid increases with the increase in depth of liquid. The pressure of liquid increases with the increase in volume. The pressure of liquid at equal depth is equal. All the gases exert pressure on the walls. The pressure is measured with a device called manometer.